Okay, so in this video, I want to talk about quasi-linear utility functions. So we're back to our consumer problem. We're trying to maximize some utility subject to a budget constraint, and the utility will take a quasi-linear shape, which my favorite way to explain that it's quasi, so almost linear. So for example, it might look a quasi-linear utility would be something like x plus square root of y. Okay. And the first question that you ought to understand is what makes for a quasi-linear. In other words, what is a general shape of quasi-linear? That's an example of quasi-linear, but what's the general shape? Well, the general shape is that there's going to be a constant times x, so that's sort of like the linear part, and there's going to be some concave function of y. Okay, that the key thing to make it quasi-linear is that this v is concave. Now, what makes something like a concave function? Well, a concave function means that the second derivative is negative. Okay. And for example, any function in the form y to the power of a, where a is less than 1, will be concave. Of course, if I put any constant in front of it, I will still make it concave. And the square root function is a special case where that a is simply a half, but we see that fairly commonly in micro courses. And I'm going to give you one of my favorite way to visualize quasi-linears. Okay, so first let's think about this special case that the utility function is equal to x plus square root of y, subject to x plus y equal, let's say 12. Okay, where x, the price of x is 1, so there's a hidden 1 here attached to, and the price of y is 1, so there's a hidden 1 attached to that. My favorite way to look at it is, again, to think about this comparison when we're thinking about how we allocate money. We think about the marginal utility of x over the price of x. That's the extra utility that we get per per 1 unit of money spent on x, and we compare that with the marginal utility of y over the price of y. This is when we have an internal solution, interior solution. And you might remember that an optimality condition is where we set these two equal to one another. We've talked a little bit about that when we talked about the Cobb-Douglas utility function. Okay, but I would like to graph this, and I have looked at this price as being equal to 1 because it allows me to do a really nice job at sort of graphing this. Well, what's the marginal utility of x? Well, that's simple. It's 1. Because that part is the linear part, which gives you a constant margin utility, right? So for every pound that you spend on X, you get an extra unit of utility. Okay, what about the marginal utility of Y? Well, it's a square root function, so this will be 1 over 2 square root of Y. I can graph this too, okay? So let's say that here, I'm going to overload this graph a little bit, and I'm going to say here I have both X and Y. Okay. And here I'm going to draw marginal utility of x. That's easy. So it's flat like this. That's my marginal utility of x. And what about y? Well, when y is very small, I get an infinite marginal utility. Okay, so tiny little bit changes a tiny bit of changes of y leads to this infinite marginal utility. So this, but note that as y goes to infinity, the marginal utility goes to 0. Okay, so this graph is going to look something like this. Marginal utility of y. Okay, and it's going to asymptote in this x-axis. You'll never touch it because it'll never be 0. Okay, um, and of course you should have known that because what did we say about the v function of y? We said that it's a concave function. Okay, so it increases but at a diminishing rate. That's why the margin utility also decreases over time, right? So it's still positive. That's the increasing part. So I get more y, I get happier, but the margin utility, the extra utility that I get, it's diminishing over time. And if you look at the question this way, you can kind of see the solution. What do I do with my first bit of money? Well, the marginal utility of y over the price of y is infinite. So I spend that on y. And I keep doing this up until, if I have enough money, up until here. So this is my y max. Okay. And therefore, you could see here that the intuition here is that you could see that with a quasi-linear, you could end up with a corner solution. For example, if you don't have enough money to purchase y max, what should you do with your money? Well, spend it all on y. What if you have abundancing money so you can purchase more than Y max? Well, you should purchase Y max and then spend the rest of the money on X. So this gives us a very good way to kind of visualize this. So the way we would normally go about solving a quasi-linear, okay, we would first find the Y max. So when we set the marginal utility of X over price of X to equal to marginal utility of Y over price of Y, which in this particular case, because I've set prices to 1, will just be simply equalizing the marginal utilities. What will come out of this is simply an expression for the Y star max, which is the maximum amount of Y that you'd want to do. And now you're at a crossroad. You can ask whether you can afford, right? Is Y star max affordable? Right? And maybe we can split it up here. And if the answer is no, then we have a corner solution. Then the Y star is simply whatever my money is divided by the price of Y. Is it affordable? Yes. Okay, then my Y star, my optimal Y, is going to be my Y star max is whatever I find. What about my X star? It's whatever leftover income. So M minus Y star max times price of Y. That's the leftover income that I'm going to have to spend on X. I'm going to divide that by the price of X. Okay, so this is how you solve a quasi-linear, and that's how you go about explaining the quasi-linear. In a separate video, we will look at the quasi-linear again, but look at it visually through the indifference curves to see if it tells us the same story. I'll see you on the next one.